Yeah, so thanks for coming out. Today's class I wanted to be like a group chat. So amongst the 3 or 4 of us, Wisha, you're gonna start, ne? You're going to share with us where you're struggling, and then we're gonna do problems around that. And then for every answer that we talk about, we discuss amongst the 3 of us. So I'll just facilitate that conversation. Where were we last night on page? No, we were on sum of a finite geometric series, right?
Yeah.
Sum of a finite geometric series. That's infinite. Convergence, divergence. These are sum to infinity. Okay. Yeah. So for Joy, it's gonna be a bit of revision, but I think it'll consolidate what she already knows. So today is new ink. Today is 2nd March 2024. Alright. Math. So let's do we're gonna do work example 13. Yeah. Work example 13. And then we are using, this is on page 34. Page 34.
Yes.
Page 34. Okay, cool. So now we have to use general formula for the sum of a geometric series, and then we have to determine an unknown k. And this is for upper bound is 8, lower bound is 1, k into a half to the power n, and this equals 255 over 64. Okay, so with sigma notation, we know that we're going to have more or less how many terms? 8 terms, but we need to first make certain of that. So it's that formula of upper bound, okay, number of terms. So it's upper bound minus lower bound plus 1, and this is 8 minus 1 plus 1, which is 8. So we're going to have 8 terms. And then in those 8 terms, we need to first let's determine the first 3 terms so that we see what the geometric sequence looks like. So we're gonna substitute from n equals 1 to n equals 3. Did you send something in the chat?
No, I didn't. I thought we did this yesterday, so I was just quickly going back
Oh, okay.
to yesterday's jam board. Oh, we ended up at example 12.
Yes.
This is 13. Okay.
So
Did it show that I opened something else?
yeah, it showed.
Oh, sorry.
With a 6-minute
Maybe
gap.
you should not give us rights.
Eh? Try and pay attention to what we're doing live. Then you can always refer to the jams later. You have access to them anyway.
Yeah, I wanted to compare. Sorry.
Oh, okay.
The steps.
Yeah, so let's do the first 3 terms for n equals 1, we'll have t1, which is, I guess, our first term, and that would be k times a half to the power 1. Remember what we talked about, the laws of exponents? If a number is raised to the power of 1, then it is itself. And then this gives us a half times k. For n equals 2, which will give us term 2. Remember our general term is Tn ar minus 1. That's our general term. So we're substituting values of n in ascending order. So now we're doing n equals 2. And that equals k to the power, or rather half to the power 2. Remember, if it's raised to the power 2, is itself multiplied by itself, which gives us a quarter of k. This is because it's 1 over 2 times 1 over 2, which if you multiply across like that, you get 1 over 4. And we do again for n equals 3, and term 3 gives us k times a half to the power 3, and this equals 1 over 2 times 1 over 2 times 1 over 2, all multiplied by k, and that's an 8th k. Then if we take out a common fact, if we have our series written out, series becomes a half k plus a quarter k plus an 8th k plus all the way to the other side. And we can take out the common factor k, and when we take it out, we're left with a half plus a quarter plus an 8th all the way. And we can go back to sigma notation and have k n equals 1 all the way up to 8. 1 over 2 to the power n equals 255 over 64. And we know that from this, let me just make it in blue. So from this series here in blue, we can work out the following. Our first term, we know it's a, it's a half. Our constant ratio should be T2 divided by T1, which is a quarter divided by a half. Remember the rules for dividing fractions with fractions. It's 1 over 4 times 2 over 1, and that gives us a half. And that's the same as T3 over T2, which is 1 over 8 over 1 over 4, which is 1 over 8 times 4 over 1, which is 1 over 2. Then we can use this formula, 1 minus r to the n over 1 minus r, and r cannot equal 1 because that will give us a 0 denominator. So we know that the nth term, because remember it's our upper bound, let me just put that in green. This n here is our upper bound, there. Then we're going to use that to say sum to the 8th term equals a half into 1 minus a half to the power 8. Yes. All of this is over 1 minus a half. And that gives us a whole lot of math to work out. So here at the bottom we have a half. And that divides this one out to give us 1. So we're left with 1 minus a half to the power 8, which is 1 minus 1 over 256. And 1 is the same as 256 divided by 256. So that can be 1 over 256. And that gives us 255 over 256. And that's what equals the sum of the first 8 geometric numbers of the geometric series. So S to the sum of the first 8 terms is 255 over 256, which is, I guess, that n equals 1 a half to the power n. Okay, so that's the sum of the first 8 terms of the series. We can then say if we multiply the sum of the first 8 terms of the series times k, because originally the question was k times the sum of the first 8 terms of a half to the power n, and the answer was 255 over 64. Then, there's a reason why I call it out like that. This part here, the 255 over 256 equals sigma notation, upper bound 8, n equals 1 of half to the power n. That part there is the same as this part here. It's this part here. So this here is 255 over 256. This here is 255 over 256. So now we know that if we multiply k by the 255 over 256, we get 255 over 64, which was the original problem. So we can then say that k times 255 over 256 equals 255 over 64. This 255 over 64 is originally where we started with our problem. We need to find k if k times this series here is that much. So now we found what this series here, half to the power n, we found what that is. And we found that it gives us 255 over 256 if we add the first 8 terms. So now that we found that out, we know that if we multiply it by the unknown k, we get 255 over 64, which is what we started with. So now to solve for k, we are going to multiply both sides by 256 over 255 such that k will equal 255 over 256 multiplied by 256 over 255, and on this side we will get
55 over 256 multiplied by 256. 64.
That's my fault. Thanks, Dre.
256
Over 256 over 255. Or multiply by 256 over 255. Okay, awesome. And then the math that happens there is that this is a multiplicative inverse. So these divide out to give us 1, and these divide out to give us 1. So you're just left with k on this side, and this divides out with that one to give us 1, and we are just left with 256 over 64, and when you punch that in your calculator, I think the answer is 4. And that's the final answer for k. So originally the question was to find the value of k, and we know that from using the sigma notation we're gonna get 8 terms, but those 8 terms, when we add them, they give us 255 over 256. So when we multiply them by a certain number, we get 255 over 64. And when we reverse work out that number, we get k equals 4. So if we roll back the tape, to when we started sequences and series, we started with first explaining a geometric sequence. Alright? So we started first with a sequence, and then we moved on to finding its general term, etc. Then after finding the sequence, we determine the series. And then in the series, we identify a few things. There's sigma notation, and then there's finite sum, and then we're gonna do next sum to infinity, where when you add the terms in the series, you get closer and closer to infinity. So that's when I think your series converges or something, but we'll confirm that as we go forward. So yeah, in each of these three, we still are using the terms from our sequences chapter for general term for both arithmetic and geometric. So general term would be a plus n minus 1 d for arithmetic series, and for geometric series it would be ar n minus 1. The same rules for the first term apply, the same rules for common difference, as well as constant ratio. The same rules for these, they still apply in each of these three: the sigma notation, the sum of a finite series, and the sum of an infinite series. So just so as we carry on into the next internal, we're gonna do maybe a couple of sums of geometric series from this problem, exercise 1.9, and and then we're gonna do infinite series.
Yeah, I'm still here.
Alright.
Sleep on the bed. Sleep on the bed.
Okay, so exercise 1-9, let's not do that, it's a proof. Given the geometric sequence, determine the 8th term, sum of the first 8 term. So let's start with number 2, right? So we have a sequence 1, -3, 9, etc. And we have to find the 8th term, T8, from this information alone. So I want you on your workbook to write down that sequence 1, -3, 9, and then we're gonna get our key data, so our first term, constant ratio, and our general term formula for the sequence. Are you doing that?
Yes, I am.
Alright, so what's our first term? What's the first term of our sequence?
Oh, 1.
It's 1, eh? Then how do we work out the constant ratio?
It's the second term minus the first term.
For a geometric sequence, that's incorrect. How do we correctly determine the constant ratio of a sequence? A geometric sequence. Constant ratio. Remember, ratio is to divide. Yes, so in geometric series we use the second term divided by first term.
Okay.
Nobuhle, just a word of advice, ne? So as we get further and further into the content, things like the constant difference versus the common ratio, they should come almost naturally. The reason for that is because the more layers you add onto the content of sequences and series, then the primary concept of ratio versus common ratio versus constant difference, they, like, if you don't grasp them early on, then the problem is gonna show up when you have to now solve. You won't be able to complete some of the problems that we have to do at this level here. So
Yeah.
So I would advise, like, focus on making sure that when we speak about a constant ratio, or constant ratio, what it is that we're referring to, because if you don't keep up with it, it might not work out well.
Okay.
Yeah. So our constant ratio is the second term divided by the first term. And for this sequence, what's our second term?
I'm blank, so you can continue now.
Okay, so our second term in our series is, okay, our first term is 1, our second term is -3, and our third term is 9. So we can have other terms after 9 all the way to the 8th term. But in this case, we have got 1, 2, and 3 terms. So our second term is -3. What is our first term? We know that it's 1. So our constant ratio then becomes -3 divided by 1, and that's -3. So then that's our constant ratio. So we've got our first term, we've got our constant ratio. Then if we use our general formula Tn equals AR n minus 1, then our 8th term would be A is 1, constant ratio is -3, and that's raised to the power 8 minus 1. And on your calculator, that would be -3 to the power 7, and that's
negative 2,187.
2,187.
Yeah.
Alright, so that would be the 8th term of this series. And then in the second part of the problem, we have to find the sum of the first 8 terms. So from n equals 1 to 8 of -3 to the power n minus 1, and this also equals sum to the 8th, sum of the first 8 terms rather. First term is 1, and then this is multiplied by 1 times constant ratio is -3, n is 8 over 1 minus -3. So this here is from that formula, the sum of the n terms is a into 1 minus r to the power n over 1 minus r, and this is 1 minus let's see, so 4, okay,
Negative 1,640.
negative 1,640. Okay, so okay, cool, that's an interesting thing. Now I want you to notice something, eh? When we calculate the 8th term, we get a value of -2,187. Why do you guys think that is?
Aren't they negative terms in like the sum?
And
I get we're adding 1 plus maybe a negative plus 1 plus a negative plus 1 plus a negative, depending on how the pattern is.
okay,
And then when we add them, some of the digits are going to subtract each other. That's why we have a smaller number
okay.
when it's a sum.
Oh, okay. When it's a sum, we have a smaller number because when
we're
we
adding,
add the positives and the negatives, some end up subtracting each other. Okay. Now, Whitley, did you hear that?
Yes, I did a little bit.
Okay. So the question is, when the first part for this sequence, when we find the 8th term of the sequence, we get a value of negative 2,187. And that's larger than when you add the first 8 terms together, all the numbers when you add them together. And the question is, why do you think that is? So Joy's answer is in the sequence you start off with the first term as a positive number, and then the second term is a negative number, and the third term is a positive number, and then the fourth term is probably a negative number because the constant ratio is -3. So it's -27. So a fourth number would be -27. So the fifth number would be how much? Times -3 would be
-27 times -3, 81.
positive 81. So you move from 1.
Yeah, they alternate. It's positive, negative, positive, negative.
Yeah,
negative.
and then you go. So if you're on a axis like this, right? Let's say that's x and that's y. I don't want to. But like I want to show how you move from one positive. No, not like that. So you go to -3, +9, -27, +81. So you swing from positive to negative in the number sequence that you follow, right? As long as you multiply by negatives. So you end up getting some negative answers and some positive answers. And when you sum them, some negative answers might be larger than the positive numbers in terms of their size, but obviously the signs are different. So let's say if you go from 9, you go to -27. So that's larger than the number before it, and its sign is also negative. But then the following number is positive. It's larger than the number before it, but its sign is different. So then the next number would be multiplied by a -3, which is our constant ratio. And it would be 81 times -3, which should give you like close to 300, if not more.
-243.
-243, okay? So then you get -243, which is larger than 80, which is negative sign, but its size is larger than 81. Yeah. So you do that 8 times. The 8th term is -2,187. So if you're going to add all of those numbers, 1, +1, -3, +9, -27, +81, -243, and you do that all the way 8 times, you'll get a smaller number than some of the terms in those 8 terms. So that makes sense because the sum of the negatives in there might be larger than the sum of the positives in the 8 terms that you're adding. And then that gives you a justification as to why this number seems smaller than that one. They're not necessarily directly related, but in some way, how the other one behaves influences the other.
I understood that.
All right. Let's do number 7. And we're given this one here, t equals 1 all the way up to n, 8.5 times t Okay, so this is what we're given. And we must first find the first three terms of the series. Okay, so we're gonna work out the first term. How do you think we're gonna start doing the first term?
Oh God.
Eh?
Yeah. Stop putting me on the spot, Bonzo.
Eh? You don't wanna be put on the spot.
No.
Oh, okay, Askies. Okay, but the first place to start is at substituting from 1 into that t over there. And we do that for this part here. So this becomes 8 times a half. For t equals 1, we'll put 1 there. And that gives us 8 times a half, which is 4. And this equals a. T2 becomes 8 times a half into, rather to the power 2. And that gives us 8 times a quarter, which is 8 over 4. That gives us 2. And T3 is 8 times a half to the power 3, which is 8 times an eighth, which is 1.
It's just one.
It's just 1, eh? Then our constant ratio, just for kicks, is also, if we take T3 over T2, we get 1 over 2. And in the same way, if we take T2 over T1, we get 2 divided by 4. This divides in there once, in there twice, and then we get also a half. Then we've calculated the first 3 terms, so we've answered that question and maybe went a step further. So the number of terms for sum to the nth term equals 7 and 63 over 64. I guess that equals what number? Multiplied by 7 is 64.
711 over 64.
511 over 64.
So make that one nice. That 11.
He's saying my one looks horrible.
The 11, yes. It looks like a 2.
It does look snaky. It did look snaky. Okay. And if you recall that other formula, a1 minus r to the power n over 1 minus r. And yes, luckily our constant ratio is not 1. So we have 511 over 64 equals a is 4. We have 1 minus
0.5.
a half. We don't have n, so I'll just put it there. And this is over 1 minus a half. So 1 minus a half is a half.
511.
Half times 4, sorry, 2 times 4 is 8. Yeah, because a half goes into 4 8 times. 1 minus a half to the power n equals 511 over 64. and then so that's
Divided by. Don't you divide 511 over 64 by 8?
yes. And how much is that? Yeah, so then we divide 511 over 64 by 8.
Yeah, 511 over 12. Over 512, so.
511 over 512 equals 1 minus a half to the power n. Then it's minus 1 minus 1, so 511 over 512 minus 512 over 512 equals negative half to the n. Okay. And then this is negative 1 over 512. What was that? Extend call. Equals negative a half to the n. How many times can you multiply 2 by itself to get 512?
256.
So it's 2 to the power 256. So it's 2 to the power 256.
I divided by 250. I divided 512 by 2.
No, not like that. I want like a cube root power thing. Like a third power, yes.
512.
Yeah, 512.
That gives me that. So should I factorize it?
Yes.
Okay.
So that is 2 times 2 times 2 times 2 times 2. So many times.
Do I do it like negative 512? Or do...
No,
Let's see if it will allow. No, it's not gonna allow.
it's let's see, 2 to the power of 9.
It says math
Yeah,
error.
so no, check. So
1024.
so if I have, oh no, here I can divide the negatives out by dividing by negative 1, right?
Yes.
So I'm just left with 1 over 512 equals a half to the power n. And this tells me that 1 over 2 to the power 9 equals 1 over 2 to the power n. And then my final answer is that n equals 9. So I'll just make a partition for it there. Partition. Therefore, n equals 9. Because if I
Did you
take...
get 9?
How did I get 9?
Yes.
I just guessed my way to the top.
You can't just guess your way to the top and leave us stranded in the desert without water.
Okay.
So
Okay.
please explain to us how you got to 9.
No, it's that, okay, so this worked example here, I'm going to refer to the worked example. Remember that one where we were doing worked example number 12, sum of a geometric series, right? And then they use this same formula that we just used here. S sub n equals a times open bracket 1 times r to the power n divided by 1 minus r. That same formula. Then on the one side where there's a power n, which is what we're looking for, on that side we get the constant ratio raised to that power n. And on the other side of the equation, we get a number that looks like it could be the base that n has, this base that n has, this one here, this base that n has. It looks like this one could be this base raised to a certain power. So that's how I started guessing it. Like, I look at that, no, but it looks like this one could be raised to that power there. And that's how you get to solve the question.
So, but you're not helping.
I'm not helping.
You're not helping. My question is, when
Okay.
I factorize it, like they did the 64 factorized as 2 to the power 6.
Yes.
Right? When I do the same thing here, it gives me maths error.
No, it shouldn't give you maths error. And here's why. Here's why. Okay. In here, in the worked example 12, right? In worked example 12. Wait, why do you say never mind? Why do you say
I
never
got
mind?
it.
No, but I want you to hear it. Please explain to us.
I think I made a mistake. I put 1 over 512.
Okay.
And then I factorized it. And then it gave me maths error. Even when I put a negative in front of it, it still gave me maths error.
Math error.
Yes.
Oh,
And then
okay.
Then at first I also divided 512 by 2, and it gave me 256.
Yes.
You understand? So now that I put 512 into the calculator and I pressed shift factorize, it gave me 2 to the power 9. And
Wait,
that's
let me
what
see
I
that
was
function.
looking for.
Let me see that function
That's
on the
what-
calculator.
512
Mm-hmm.
is equal to, you press equal to, and you say shift factorize. I don't know what these things are called.
Oh, those are degrees, minutes, seconds.
Yeah, that.
But that's when you're doing those kinds of calculations, like in geography and land surveying.
Yeah,
But-
not yet there, but that's what I got.
Oh, okay. I didn't know this calculator had this function. That's so cool.
I don't know if Nova's calculator has it.
I see. That's so. I think the calculator she's using works almost akin to this one. So I have to say, if I'm to guess from 2 to the power 7, how much do I get? Okay, 128. Maybe that's not what I want. 2 to the power 8, how much do I get? Okay, maybe I'm getting closer. And then I say 2
It
to the
takes time.
power.
And that's the value.
Like, okay, cool.
So I
5
don't
12.
have enough. 3 hours is not a lot.
It's not, because it's just over 1 minute for every mark. Yes, so it's not a lot of time to guess like that, unless you do it really fast and you just land on the correct answer.
Then don't forget it.
No, she didn't.
No. So here's the thing, we're arguing. So
We're not arguing.
when we're talking
Pointing
about,
We're pointing out. It's not an argument.
we're not arguing. Yes, we're talking about how So to get to the answer of n equals 9, right? If you scroll to page page 33 of our learning guide, there's that problem that we did, right? And it's a similar problem to this one which we just did. I think it's in the jam. I'll just open the jam. Oh no, why did it close up? Okay. Why did it close up? Friday math class. Okay, cool. Remember this problem. This is showing on your jam, right? Is this the jam that's showing?
No, we're still on the previous exercise.
On the previous one. I want you to open our jam from last night. Can you do that for us?
Yeah.
And then open page 6 of it.
Yeah.
You opened it, ne?
Factorization, I did.
Yeah.
Uh,
So you remember this part here at the bottom here? On page 6.
yeah.
Remember that?
Yes.
So I want you to look at that. You see there we've got the final answer n equals 6, right? And that's because on the one side of the equation where we use the sum to the nth term equals a times 1 minus r to the n over 1 minus r. And we use that whole process right up to where we get negative 2 to the power n equals negative 2 to the power 6. So we got negative 2 to the power 6 because in the step just before, we have a number that is 64, right? But what number can we multiply by itself so many times that we get 64? So we have to now factorize 64. Remember what we talked about factorization here? Take out a common factor and you have to take it out so many times that it multiplies itself, or rather gives you that power. So the number of times it multiplies itself by is this power here, the 6 here. So we've then discussed that it's negative 2 multiplying itself 6 times will give us 64. So negative 2 times 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 negative 2. So negative 2 multiplying itself 6 times will give us 64. And that's how we got to factorize 64 as negative 2 to power 6. In the same way, just going back to today's math class, in the same way, this problem is factorized so that 1 over 512, this part here, is the same as 1 over 2 to the power 9. It's the same way we're factorizing. Alright, so have you opened today's workbook, the one we're just doing now?
Yes, I'm on it.
Oh, okay, yeah. So on page 6, that's where we are now. So the way that you factorize that 1 over 512 is the same as the one in workbook, worked example number 12 on page 33 of the learning guide.
So is there a better way that you can explain this?
I'll have to think of one.
Because you're kind of like complicating it even
Okay.
further. In my opinion, because like I still don't understand how you did that.
Like I said, I guessed it. Because, while I intuitively understand that it's a factor, like you have to factorize the 512, like you understand that you intuitively have to factorize that. But now you can do trial and error, and if you can do it quickly, then you get to the answer quickly. That's how in my mind I processed it.
I don't get how you did that. Like, I still can't comprehend how you did that because yes, you guessed.
Yes.
But by the time you got to 512,
Okay. Sure.
can you please find a better way to explain this so we all understand?
Yes, I'm thinking of one. But I don't know how else to explain factorization. I have to find another way to explain factorization. But and there's a whole lot of ways that factorization can occur. Yeah, so I wanted to share some notes on factors, right? So let me just change the color. And
You're
start.
still on the same Jamboard.
Yes, the one year today. So I want us to discuss factors, right? And this you'll find in that grade 9, grade 10 math book. When you are dividing, right? Or let's say you're adding. Let's say you're adding a half and a quarter, right? From just looking at these numbers, it doesn't look like you can just off the bat add them like that. That's incorrect. So we don't do like that. It's not the correct way of adding numbers, right? So adding rather fractions. So what we do is we look for a lowest common denominator. Lowest common denominator. Now, a denominator is the number that divides a certain number, right? So the lowest common denominator here is 4. Why is that? Because this denominator 2 can divide into 4 and it goes into 4 twice. And this denominator 4 can go into 4 and it goes into 4 once, right? So how we then divide is we say how many times does 2 go into 4? It goes twice. And then we then reverse the calculation, but this time again we go upwards. And then we say 2 times 1. So here we start off with dividing the denominators and then multiplying the numerators. So after we say 2 times 1 is 2, then we put that there. And then we drop the sign as it is. So if it's a negative there, you drop a negative sign. So we say plus. And then we ask ourselves the same question again. How many times does 4 go into 4? It goes in there once, right? So now we find that it goes into 4 once. Now we take that once and we multiply it by the 1 there. And we multiply 1 by 1 and we get 1. Now our final answer then becomes 2 plus 1, which is 3 over 4. And yes, if we go onto a chocolate bar like that again, that isn't cut out into pieces, and we have one Kit Kat looking slab there, and then maybe longanyana ones, half Kit Kats, and then the other slab of the Kit Kat is divided 4 times. The other slab of the Kit Kat is divided 8 times, right? If this here is half,
Emagancane, you're just lagging quite a bit.
okay,
I don't know how it's gonna catch up. Let me just refresh my page. Okay.
it says you joined. Okay, is it better
I've
now?
joined. The bar isn't even there. Okay, there you go.
Is it there now?
It just appeared now.
Okay, so here, if we take a half a bar, right, and we add a quarter of a bar, so we take a half and to it we add a quarter. Do you realize now that if we take that half, I'll just make it in red. If we take that half and we add to it a quarter. So we'd say this quarter is added now to that half there. You see now we do get 3/4 because then I'll just make it blue. So when we add a quarter, that's it. When we add a quarter to a half, then we end up with 3/4. And this is how we do the math, right? So we look for lowest common denominator. Now what that lowest common denominator actually is that it is a, like you could think of it as a factor in and of itself, and like a factor of itself, a factor of itself, and it's also like 2 is also a factor of it.
Okay.
Like 2 is a factor of 4 because if you multiply 2 by a factor of 2, you get 4. You follow?
Yeah.
Yeah, if you multiply 2 by a factor of 2, you get 4. So what happens if you multiply 2 by a factor of 2 by a factor of 2? No, we're multiplying, not adding. So let's say we've got 2 by 2 by 2. So we're multiplying 2 by a factor of 2. And then we multiply it again by a factor of 2. What do we get as an answer? Right now, this one's very easy.
32.
No, wait. We multiply 2
4.
by 2. That's
Yeah.
4. By another 2, how much do we get?
16.
That's if we do it 4 times.
Yes.
Yes, that's if we do it 4 times. So I want you to do it 3 times. Just 2 multiplying itself 3 times. So it's 2 times 2 times 2. So you count 2 3 times in that math.
Yeah.
How much do you get?
Why do you get an 8 and I don't, and I'm using a calculator?
Wait, because maybe you're not understanding what I'm saying or something else. But my question is, the instruction rather is take 2, multiply it by a factor of 2, then multiply it again by a factor of 2.
It's 8.
It's 8. Then when you do the same math, but you do it starting with 2, then multiplying it by another 2, then by another 2, and then by another 2.
Yeah.
How much does that give you?
32.
How many times did you multiply 2 by itself?
5.
Okay, the instruction was to do it 4 times. So your math is not incorrect. The instruction was to do it 4 times because we're doing
But
it
you've
in.
already moved on from that.
I agree. We did the third. We did 2 to the power. We did 2 multiplying itself 3 times, and then we supposed to do it 2 multiplying itself 4 times, and then 5 times, and then 6 times, so that we realize the pattern. You check. So when we visualize the pattern, so like where I started was with, if you look at the denominator 4, right, when you're dividing and adding fractions or subtracting fractions, 2 is a factor of 4 and 4 is a factor of itself. So because of that, if you take 2 and you multiply it by a factor of 2, you get 4. So that means we can grow or shrink a number by multiplying it so many times by a factor. But if we're just going to do one number multiplying itself or being multiplied by itself as a factor, then that is the same as raising the exponent. So if you look at our Jamboard, I started off with 2 to the power 3, and towards the right, I wrote it out multiplying itself 3 times, right? And if you look at the next one, raised to the power 4, then to the right, it's its number, it's the same number multiplying itself by itself as a factor 4 times. And if we use a different color, maybe here, then that number multiplies itself out by itself as a factor, so to speak. It's just, I'm not really sure if I'm using the correct words, but I'm trying my best to just plainly put it. That one. So when we can think about factors from a fractions perspective, and we can also think about factors from an exponent's perspective, right? And this second way from an exponent's perspective is exactly how we get to finally answer this kind of problem, where if we have a number, in this case a constant ratio, raised to the power n, then we can factorize what's on the other side of the equation that's numeric, by thinking of the numbers like this. Am I still lagging?
Yeah.
So that means there's stuff you're not seeing was there.
Yeah. So that's why I was just refreshing.
Ish. Okay, but on page 7 of this Jamboard, do you
Yes.
see at the bottom there I wrote there 2 to the power 3 is 2 times 2 times 2, and that gives you
Yes.
8. So 2 being a factor of 8 means that it has to multiply itself out 3 times to give you 8. 2 being a factor of 16 means it has to multiply itself 4 times to give you 16. Why did I write 25 here? It's supposed to be 32. 32. Yeah. So 2 being a factor of 32 has to multiply itself 5 times to give you 32. Let me check. So because of thinking like this about numbers or factors, you can factorize a number such as 64 as negative 2 to the power 6, or 1 over 5 12 as a half to the power of 9. Yeah, 1. So this is the kind of math or factorization that allows you to be able to solve these types of numeric problems. You get me? Yeah, so we'll end this 1 year math for now here, and then we'll shortly we'll do physics at 1. Ne?
I quit.
Hi, bo.
If the only thing I could understand in this lesson was factors and exponents,
Oh no, the thing is at matric, factors and exponents ought to come almost intuitively. That's the expectation. That's the
Okay,
expectation.
don't quit. Who am I going to attend classes with? Don't quit. Don't quit on us.
Yeah, so that's the reality of like pure maths for matric. At this stage, the stuff from grade 9, you're expected to know it intuitively. So you also ought to be able to use the same tricks to manipulate those problems that you find in matric. Like, you are allowed to use any trick of the book that you've learned from when you started doing maths. And I keep saying this because it's just how it is. It's cumulative knowledge. You know, it's called cumulative knowledge for the simple reason, even if you're doing a PhD in math, you're expected to remember a trick that you learned when you first started math. And that's just what it is. And at that level, some things are expected intuitively. You're expected to just know them. But like I say, practice and pushing yourself as well. Self-study, nothing beats self-study. Nothing beats self-study. So I'll see you at 1 for science.
Yeah, then I quit.